All right. Am I bouncing? Yeah. All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. Yes. So 2910. Come on. Stupid lid. It's not a fair fight. It's not a fair fight, I tell you. All right, so we are continuing our discussion of Galois theory. And basically at the moment, we're just trying to build up some examples that will exhibit the structure of the fundamental theorem. Just 4? Why is there? Oh, there's 5. 6753. So we're going to look at some examples today which illustrate the fundamental theorem of Galois theory, which hopefully we will state at least next class, and we'll prove parts of it. We probably won't prove the whole thing. A lot of things to prove here. We won't actually prove all of them, but hopefully we'll look at enough examples and prove enough of it that you'll understand. Okay. So we talked about. Remember the story here. We had an extension E over F, right? And then we talked about aught K over F, which was what? K. This was the what? Like sigma going from K to K, right? Such that sigma of x is equal to x for all x in F, right? The F fixing, the so-called F fixing automorphisms of K. And we studied that a little bit. We said a few things about it. Our proposition 1, just to recap, what did proposition 1 say? It said that aught K over F subgroup, right? It is a subgroup of the automorphisms of K. Is one thing we learned. Proposition 2, what did it say? It said if we have K over F with alpha algebraic in K, then sigma in the field, the F fixing automorphisms of K, permutes zeros of f of x in, with coefficients in F such that what? F of alpha equals to 0, right? In other words, f of alpha equal to 0, we said implies that f of sigma alpha equal to 0, right? In particular, if you're looking at the minimal polynomial, then if you got one of the zeros of the minimal polynomial, you must have all of the zeros to the minimal polynomial in the algebraic extension, I suppose, because you can look at these F fixing automorphisms and move one zero to the other, right? I guess that's not just true for minimal polynomials, right? It's just true for polynomials. If we have 1, 0, we have to be able to generate all others by, well, I guess you don't have to be able to generate all others, but whatever you do generate has to also be a 0, let's say that, right? there's no guarantee that sigma acts on alpha in an interesting way. It could just fix it itself, I don't know. All right. That was proposition 2. We looked at some examples of this. We actually calculated the F-fixing automorphisms of a couple of examples. That led us to proposition 3, which we've also proved in the previous class, but I'll state it here again, since it's been a little bit since we did it. If H is a subgroup of the automorphisms of K, all right, then the collection F subset of K such that F is fixed by H is a subfield. Okay, sorry, my handwriting degenerates. In fact, that brings us to a definition, which I'll state again here. Definition. All right, so here's the context. If H is a subgroup of the automorphisms of K, then the subfield F of K, which is fixed by H, is the so-called fixed field of H. So like anytime you have you can look at a subgroup of the automorphism group and then study, the set of all elements, set of all automorphisms which are fixed by that. The set of all. Oh, I'm sorry, guys. Words are escaping me now. Did we actually prove this? I'm not sure we actually proved that proposition 3 yet, did we? Yeah, we did. Yeah, we did. That was the one where we looked at. We can look at the proof right quick. Let's just study this momentarily. Suppose we have what's in the definition, right? So let's look at it. Let's let H be a subset of the automorphisms of K, and suppose that sigma and let's suppose that alpha. I don't know. I need 2 letters. Sigma and gamma are both elements of instead of, let's say, A and B are elements of K such that what? For any sigma in H, we have sigma of A equals to A and sigma of B equals to B. So we have a subgroup of the automorphism group, and we're looking at elements of K which are fixed by all of the automorphisms in the subset H. I know who's the bad influence here.
He is breathing so
breathing so loud? Okay. Squishing your head, crushing your skull. Sorry. Let me stop making obscure references here. Where was I? So these are two elements of K, which are both fixed by H. And the claim is that if we look at like AB, right, and we look at an arbitrary sigma from this subset of the automorphisms, well, sigma of AB would be what? If it's an automorphism, well, this is sigma of A times sigma of B, right? But that's equal to A times B. So as you can see, the product of two such A's and B's is again fixed, right? So saying that AB is in K, I said it this way to try to not make it look circular. AB in K such that we have this. This is to say that A and B are in the fixed field. All right. And I'm hesitant to say this, but I think another notation for this is K upper H. Let me not even write it. I need to check on that. There's a kind of neat notation for the fixed subfield, which, you know, like this notation F. F is the fixed subfield of K. Well, it doesn't tell you that F has any attachment to the, you know, the extension field K. Like, what is K to H, you know? I think this might be the notation, but let me just waffle on that a bit until I have a chance to refresh my memory on the notation here. I'm sorry, guys. I'd like to be more committal to that, but there's got to be some good notation for the fixed field of H. All right. Now, so that shows what? This shows that if A and B are in F, then AB is also in F, right? And also, because this is true not for one sigma, but this is true for what? For all sigma in the H, right? You need that every single stupid automorphisms in the subgroup fixes the thing in the fixed field. And of course, if we look at sigma of A inverse, well, that's sigma of A inverse because it's an automorphism. I mean, it's a homomorphism, so that's true, but that, of course, is A inverse, so there you go. I mean, it's closed under multiplication and inversion. So we can prove, in fact, the fixed subfield is indeed a subfield. All right. And if you look at it, we didn't really use the fact that H is a subgroup here at all, right? But what's of principal interest in the study of Galois theory is subgroups, because we're gonna study the correspondence between these fixed subfields and like subgroups of the automorphism group in a particular sense. Yeah.
What we just did, though, is pretty much, it's pretty much the subgroup test, right?
Mm-hmm.
I mean, that's pretty much what we just did.
I think I'm using the sub, I mean, you might call it the sub, oh, why did I do that? The sub.
That's what I was wondering. I don't remember us ever learning like a
Well,
sub test or
right, I think subfield test should be some, I may be neglecting something here. I think I need to show, what's the test for being a subfield? I think we need to show it's a subring, right? And has one in there.
But then every element has an inverse. Right, of our multiplicative inverse.
Yeah, every non-zero element has a multiplicative inverse. Should be closed under addition and subtraction, I suppose.
That is under the subring test.
Yeah. Okay, so proposition 4. It says that the association of groups to fields and fields to groups defined above is inclusion reversing. So, number 1, if we have that field 1 is a subset of field 2 is a subset of K, all right? Then the automorphisms of K which fix field 2 are in fact a subgroup of the automorphisms of K which fix F1. So this is inclusion reversing. Notice that the F1 is a subset of F2, but the automorphisms which fix F2 are a subgroup of those which fix F1. So it's inclusion reversing. And also, too, if H1 is a subgroup of H2, is a subgroup of the automorphisms of K, all right, and F1 and F2 are associated fixed fields. In other words, if we're so bold as to assume I've remembered the notation right, you know, there's like about a 50-50 chance I'm right on the notation. So let's just throw caution to the wind and hope I don't have to make a comment to this video. KH1 and F2 is the fixed field of H2. All right. Associated fixed fields of H1 and H2, then, well, F2 is a subset of F1. Yeah.
Is the proof of this pretty like?
One line, yeah.
Well, no, that's not like that. Like, I don't understand why it would why the automorphism can reverse the subset subgroup.
Okay, so let us suppose that F1 is a subset of F2. Is, you know, these are all inside some extension. These are all subfields of K, all right? And consider sigma to be an element of the F2 fixing automorphisms of K. Right? What does that mean? So what privileges does this entitle us to? This says that sigma of x is equal to x for all x in where? F2, right. So let's let y be an element of F1, which is, by the way, a subset of F2, right? Therefore, y is an element of F2, and so sigma of y is equal to y. But y was an arbitrary element of F1, which shows that sigma fixes F1. So we just took an arbitrary one of these guys and showed it was one of those guys, which is to say that that's a subset of that. A homework problem that I assigned you guys in linear, which is like this, if you remember, there was a problem about annihilators and or like subsets and their duals, and we saw like the annihilator idea sort of had this sort of inclusion flipping idea as well. I mean, this sort of reversal of subsetting is not without precedent. Like, if you think back, we've had problems before that worked like this, but anyway, it's true. I will not prove to in the interest of spending time on examples. So, all right. Actually, at this point, I'm going to go ahead and go on to proposition 5. We'll get back to the examples in due time. So can I erase that? I need to, actually, well, I should probably put over here. All right, so proposition 5 says the following. It says let E be splitting field over F of polynomial f of x with coefficients in F, then the order of the automorphism group, the F-fixing automorphisms over K, is less than or equal to the degree of the extension of E over F. With equality, if f of x is separable over F. All right? So if we have a splitting field, then we can be assured that the size of the F-fixing automorphisms are at most the degree of the splitting field over the base field. All right? And that brings us to the following definition. Let K over F be a finite extension. All right. Then K is said to be Galois over F. All right. And K over F is a Galois extension. All right. If what? If the size of the automorphism group, of the F-fixing automorphism group, if aught K over F, all right, is equal to the degree of K over F. And in this case, if K over F is Galois, then the group of automorphisms aught K over F is the so-called Galois group in this case. Gal K over F equals aught K over F. And that's the so-called Galois group of the extension. All right. What have I done? Is the breathing? Mm-hmm.
So does that mean, does Prop 5 lead to the definition? Does that mean that K is the splitting field over F?
Ah, corollary. Corollary 6 says the following. It says if K is the splitting field, all right, if K is a splitting field over F of a separable polynomial, f of x, all right, then k over f is Galois. He says, furthermore, we shall see in the next section that the converse is true. And that will completely characterize Galois extensions. All right. So in the next section, we complete this thought. We can only have half the thought here. If we have a splitting field with a separable polynomial, then it's Galois. But the next section says, if this is Galois, then guess what? If this is Galois, then that means that it's corresponding to a separable polynomial, and the extension is a splitting field of said polynomial. But that's the next section, okay? So at the moment, we just say this direction. Yeah. Now, so here, I've told myself to read this verbatim, so I will do that. Notice also that corollary 6 implies that the splitting field of any polynomial over Q is Galois, since the splitting field of f of x is clearly the same as the splitting field of a product of irreducible factors of f of x. All right. So in other words, if you had something like f of x is equal to, I don't know, x squared plus 1 squared, you know, times x squared minus 2 to the 15th power. If this was your stupid polynomial, right? Over the rationals, what's the splitting field of that polynomial? So to calculate the splitting field, you look at the separable polynomial which underlies the given one, right? Basically delete extra copies of whatever your irreducible factors are. So to find the splitting field of this, I would just consider g of x equal to x squared plus 1 times x squared minus 2. To split this, I need an I. To split that, I need to square root of 2. If I take q adjoin I in the square root of 2, that's going to be a splitting field for that polynomial. And since it's the splitting field of a separable polynomial, the point is, the f of x that I have up in the corner there is not separable, right? It's got repeated roots. But that's really not, I mean, you can still say things about it. You just have to go, okay, well, I can find the corresponding separable polynomial by just getting rid of my multiplicities, right? Because anything that splits the separable polynomial underlying f will also, I mean, if g is split, then of course this is also split, right? Because you can factor in the same way here as you can there, In other words, this k is the splitting field of a separable polynomial. Okay, it's g of x in my upper right, for my silly example to illustrate the comment here at the bottom of page 562. So that is a Galois extension of the rationals, because it is the splitting field of the separable polynomial g. All right. What I want to look at is some examples. All right. Hopefully I have, yes, I should have time. Good. So I'm going to go ahead and start with example 1, which is q adjoin the square root of 2 over q. He says this is Galois with the Galois group what? We worked this out the other day, right? Remember, we worked out that the Galois group here was basically 1 and sigma, where sigma was defined by sigma the square root of 2, equals minus the square root of 2, right? That we extended that to define an automorphism on Q adjoin root 2, which when we compose it with itself is the identity. So if you look at it, the Galois group here is up to isomorphism, the cyclic group of order 2. And I can see, how do I know that extension's Galois? What does it take for it to be a Galois extension? The degree of the F-fixing automorphisms, right? The degree of the F-fixing automorphisms is equal to the degree of the extension. I should say the order of this group is equal to the degree of this extension. What's the order of the group? It's 2. What's the degree of the extension? It's also 2. So, Galois. Great. 2, this one's more exciting. Actually, this is 4. I'm skipping ahead to 4. Perhaps I should, oh, fine. I feel guilty. 3. 3 is a non-example. 3 is a non-example. It's actually important. You're like, make up your mind. Hey, by now you should know I can't do that. All right, so if we look at Q adjoin the cube root of 2 over Q, what's the degree of the extension? Remember? The degree of the extension is 3, right? Because x squared, this is, this is the minimal polynomial, remember? Over q of x is what? X cubed minus 2, which is irreducible by Eisenstein and p equals to 2. And this is an extension based on that. So it has degree 3. Yet what did we calculate the F-fixing automorphisms were the other day? Do you remember? We worked it out. The only thing in there was the identity. So the order of the Q-fixing automorphisms of Q adjoin the square root of 3 is 1. 1 is not equal to 3, therefore this is not a Galois extension. All right? Let's look at 4 finally. So this is Q adjoin the square root of 2, square root of 3. Look at that over, let me call this thing K over Q, all right? So is this Galois? So let's see here. Basically, to understand if sigma is an element of the automorphisms of K, which fix Q, we need to describe what does it take to describe those automorphisms. We need to say what happens, this is fixed by action on what? Well, square root of 2 and square root of 3, right? Whatever happens to square root of 2 and square root of 3 defines what the sigma is, right? And if you think about it, we must send the square root of 2 to an element of the same kind. We must send the square root of 3 to an element of the same kind, right? And when we sort through those details, that means that this has to go to plus or minus root 2. This has to go to plus or minus root 3. So there are really 4 different things you can do, right? You can talk about 1, which is going to be root 2 goes to root 2, root 3 goes to root 3, right? You can talk about sigma, which perhaps would be root 2 goes to minus root 2, and root 3 is fixed. You could talk about tau, which would be maybe root 2 is fixed, but root 3 maps to minus root 3, right? And you could look at, well, sigma tau, right? Sigma tau would be what? Well, how would that work? Right? If you do sigma and tau one after the other, you're going to swap the signs in both of your roots. Each one of these 4 cases defines a possible automorphism of the field. You know, is it actually an automorphism is a question that you have to work through the details of. Like, just because you send generators to generators doesn't mean you're respecting the other things that define the field. You got to be careful. But these do, in fact, each define a Q-fixing automorphism of K, all right? And that's everything, because that's all the possibilities, because the K is generated by root 2 and root 3, right? These are the only, combinatorially speaking, I know you don't trust me when it comes to combinatorics. I've shown myself to be far from trustworthy on this point, but I read it in Dummett and Foote, so it's probably okay. But the good news is here that each one of these, right, you can check it out. Sigma squared is what? Tau squared is what? Sigma tau squared is what? Think about it. If you do them twice, they just send both generators to themselves again, because they swap the minus sign back. Or they swap both of the minus sign backs for the third one. In other words, I'm saying each one of these automorphisms has order 2. So what do we have here? What's the order of the, and these are also distinct, right? It's clear that these are distinct automorphisms. So if I write down that the automorphism group of K over Q is formed by 1 sigma tau and sigma tau, that is a group of order 4. Group of order 4, right? And what did we work out the other day? What is the degree of K over Q? Remember, we spent some time working on this. We figured out that the degree of this extension is 4, right? Therefore, this is a Galois extension, because the order of the Galois group, well, the order of the Q-fixing automorphisms of K is equal to the degree of K over Q. That makes this a Galois extension. And it is useful to make a picture which studies the interplay between the fields and the groups here. Let's try to make that picture. I'll make it over here, because I think we don't need this anymore, right? Like famous last words. All right, so here's my attempt. We'll have Q adjoin the square root of 2 and square root of 3 up here. All right? Then what do you have? You've got your Q adjoin the square root of 2 subfield. You've got your Q adjoin the square root of 3 subfield. What's the other subfield? I mean, there's Q down here, right? Square root of 6, right? Q adjoin the square root of 6 is another handy-dandy subfield here. In contrast, if we look at the trivial group 1, what does 1 fix? the identity automorphism sends what to itself in terms of fields? The identity sends everything to itself, right? So the fixed field of 1 is this. I mean, not debate whether or not I got the notation backwards. We'll fix it in a future class. My apologies if I've gotten it backwards. All right, so what else is there? What are there? I mean, down here somewhere, there's gal K over Q, which was what? 1 sigma tau, right? And you have subgroups. You've got the subgroup generated by 1 sigma. You got the subgroup generated by 1 tau. You've got the subgroup generated by 1 sigma tau, right? Notice that I've drawn the picture for the subgroup lattice upside down. Like a lot of times we would draw the biggest group at the top and then put the identity group at the bottom. I've reversed that pattern so that we can see the correspondence. Like what is the fixed field of the subgroup 1? What's the fixed field? I still may have messed up the picture. Fixed field of 1 sigma. What is sigma? Sigma of, what? Something of the form A plus, what is sigma fix? It fixes root 3, right? So sigma of A plus B root 3 is A plus B root 3, right? So the fixed field of this is Q adjoin the square root of 3. So let me fix my picture. Right? This, if I put 1 tau here, is going to fix that one, right? And sigma tau fixes the square root of 6. So there's a correspondence between the subfields of a Galois extension and the subgroups of the Galois group in this way. This is made more precise by the fundamental theorem of Galois theory in section 14.2. All right, I can be less fuzzy about it than I am being at the moment, but yeah. Another example is the splitting. Okay, great. Well, this didn't go well, but 5 is sort of the natural counterpoint to 3. 5 says look at K equal to, Q adjoin rho and the cube root of 2, where rho equals to e to the 2 pi I over 3, right? In other words, this is the splitting field of what? Of x cubed minus 2, right? This is the splitting field, and what's the degree of the splitting field of x cubed minus 2? I mean, remember we found in our previous work that the degree of k over q was what? We calculated it was 6. Remember that? We did that. Well, he works out here from page 564 to 565 the mechanics of the Galois group. Basically what he shows is that if we let sigma be the permutation which does what? Sigma is defined by the following. It sends the cube root of 2 to the third root of unity times the cube root of 2, and it fixes the third root of unity, primitive third root of unity row. If that's my sigma, and this is my tau, and I let tau kind of do the opposite thing, it fixes the cube root of 2, and it sends the third root of unity to the sort of other third root of unity that's primitive here. In other words, it sends rho to rho squared. Remember, rho squared is the other generator for the third roots of unity, which is, by the way, equal to -1 minus rho. Anyway, defining sigma and tau is that. Works it out, and he works out that the automorphism group of K, which fixes Q here, is basically equal to, and I'll use generators and relations, sigma tau, such that, well, let's see here if you remember this one. Sigma tau such that what? What's the relation? Sigma cubed equals to tau squared equals to 1, and sigma tau equal to tau sigma squared. Can you recognize what that is? What's the Galois? Well, am I allowed to say that this is the Galois group? Is this extension Galois? I don't know if you can see this or not, but what I'm describing right now is S3. This is the generators relations presentation of the symmetric group on 3 symbols. Right? Basically, sigma is the 3 cycle, tau is the 2 cycle, and they're interacting as they're supposed to. So this is nothing more than S3 up to isomorphism, which of course has order 6, which means yes, this is a Galois extension. And this time, the Galois group is non-abelian, right? Because the symmetric group S3 is non-abelian. So after all of this, he has this like throwaway sentence, which will make you pull your hair out if you've got something to pull out. He says like, oh, but we already knew it was S3. Because why? He's like, because the splitting field permutes the roots of the, how does he say it? The splitting field permutes the roots of what? Let me not mischaracterize his sentence here. He says, alternatively, and less computationally, since G, since the Galois group acts as permutations of the 3 roots of x cubed minus 2, it is a subgroup of S3. And it must be S3 since its order is 6. How does he know its order is 6, though? How do you know that the Galois group has order 6 at that point?
You know, like we did in abstract, where you just calculate everything. Because there's only so many things to do if sigma to the third and tau squared is 1, right?
Yeah, I'm not disputing, like, we could do explicit computations to prove that that's S3, no doubt, no doubt. I'm just wondering, how did he know that the extension is Galois without knowing that the automorphism group had order 6? If I knew the automorphism group had order 6, and I knew that it acted as permutations on 3 roots, then I would know that it has to be S3 up to isomorphism. But how do I know that with what's given in the example, ignoring the computations, how do I know that it has order 6? Maybe, I'm not, something to think about. But then the next example, example 6, he looks at example 6, he looks at this field, this tower Q, over Q adjoin square root of 2 over Q adjoin the fourth root of 2, all right? And he says that Q adjoin the fourth root of 2 is not Galois over Qy. Since any, let me call that K, any automorphism, any sigma in automorphisms of K is governed by what? Where it sends the fourth root of 2, right? So the fourth root of 2 can either go to, what are the choices for fourth root of 2? It can either go to the fourth root of 2 minus the fourth root of 2, or what are the other choices? I times the fourth root of 2, or minus I times the fourth root of 2. But what's the trouble with that? Oh, I see. You see the trouble? It's the same trouble we had with example 3 when we worked out the details before. We only had one automorphism of Q adjoin the square root of 2 because the other two roots were complex and we can't send, I mean, we're not allowed, those are not in K, right? So you have at most a Galois group of what? Of order, I mean, your Q-fixing automorphisms of K have at most 2 elements. So this implies that ought, and I think it actually does have both. So like ought K over Q is less than or equal to 2. I don't even care if it's equal or not. I don't really much care. The point is it's not what? It's not 4. And we know that the degree of Q adjoin the fourth root of 2 is degree 4 as an extension of the rationals because x to the fourth minus 2 is irreducible by Eisenstein p equals to 2. Therefore, this is not a Galois extension. What's interesting about this example, and the reason I'm ending with it today, is that both of this, if you look inside here, Q over this right here is a Galois extension. See this? There's something interesting here. This is a Galois extension. And this also is a Galois extension. Because you can prove that any degree 2 extension over a field not of characteristic 2 is necessarily Galois. Because the base field fixing automorphisms are just governed by where you're sending your square root to. You send square root d to d, that's the identity, square root d to minus d, that's the sort of conjugation map. Those together form the group of base field fixing automorphisms of a degree 2 extension, which has order 2, and it's equal to the degree 2 extension. So that means it's Galois. So degree 2 extension is Galois if we're not working over base 2, excuse me, characteristic 2 field. This is interesting because it shows us that the Galois extension of a Galois, the Galois extension of a Galois extension isn't necessarily Galois. So properties of Galois extensions are a little bit, they're not as dumb as some of the things you've seen before in math, right? There's going to require a little bit more. But that isn't to say that there's not things to say. We'll see in section 14.2 there's many things that can be said. So anyway, that's it.